please.
It's my great pleasure today to present the SO-CHIC project. SO-CHIC stands for Southern Ocean Carbon and Heat Impact on Climate. It's a project funded under the Age 2020 program of the European Commission, and I'm the scientific coordinator. So SO-CHIC, as the name says it all, is interested in carbon and heat of the Southern Ocean. And so I'd like to start this broad overview of the project by some motivation about why we should care at all about the Southern Ocean. There's many angles actually to address that question, and the angle I'd like to take today is the concern about global climate. As you probably all know, the Earth has been warming at an unprecedented rate in at least the past 2,000 years. That's an important result of the last IPCC report. And what I will argue in the coming slides is that the Southern Ocean actually partly controls that rate. So to try to demonstrate that, let me consider a very simple Earth energy budget, which basically tells us that global warming depends on three different ingredients. First, radiative forcing, which is basically the greenhouse gas concentration in the atmosphere, minus whatever energy is taken away from the atmosphere by the oceans, and all that modulated by what we call physical climate feedback, which are mostly atmospheric features. What I'll show now is that all of these three terms that control global warming are strongly influenced by the Southern Ocean. For radiative forcing, the concentration of greenhouse gas in the atmosphere depends strongly on the ocean natural sink, which basically take up about 25% of human emissions. And when you look at where the carbon enters the global ocean, you quickly realize that the Southern Ocean is a key player by taking up to 40% of carbon to inject it in the global ocean. Now, when we look at heat storage, the figure is even more striking. About 70% of all the heat that entered the global ocean in the past 60 years entered through the Southern Ocean door. And when we look at climate feedback, I say that's mostly atmospheric processes, but those are actually strongly influenced by the ocean temperature, and in particular, the Southern Ocean temperature that control what we call the low cloud feedback. And so that means that's local processes taking place in the Southern Ocean to set up the upper ocean stratification and the large scale circulation will actually be instrumental in setting those climate feedback. And so in summary, the local processes occurring in the Southern Ocean have a strong impact on all of these three terms and therefore on setting global warming rates. Now, we know that Southern Ocean is changing rapidly. There is a strong warming at depth of the Southern Ocean water. This warming impose a melt of the ice sheet, which release fresh water at the surface of the ocean, change the circulation. There's also change of the chemistry with a strong acidification associated with the carbon uptake. And therefore, there are questions emerging today on how much the Southern Ocean will be able to keep up to continue in the same way to control global warming rates. So for all these reasons, we started the SO-CHIC project, which aims at understanding and quantifying the variety of heat and carbon budget in the Southern Ocean. So how do we do that? First thing is we put together a great group of scientists, about 50 scientists across 16 institutes, spread across 10 countries, mostly Europe, but also South Africa. And we set up a program which is based on a combination of observation and numerical model, really looking at key processes from targeted experiments and high resolution model simulation, all the way to climate impact by looking at long-term monitoring or a system model. The four key processes that we identified and that we focus on in this project, we identified as blocking or advance in understanding the role of the Southern Ocean and climate are First, RC fluxes, which basically control the rate by which climate signal can be transferred from the atmosphere to the ocean. And then all the processes that allow for surface climate signal entering the surface to be propagated in the deep interior. And that can occur by upper ocean ventilation or bottom ocean ventilation, or also by what we call abrupt chocolate events, which are basically deep convection occurring in open ocean Polynia in the Southern Ocean. Once we have a better understanding of these processes, we try to estimate their large-scale effect, in particular on large-scale atmospheric circulation, and also on ocean heat and carbon change and decadal change. We also have two work packages in the project to really link with the stakeholder by a strong work on data management, to have an open and free data access, and also with a last work package on management and dissemination, which is a very important part of our project, and many policy briefing, press briefings have been organized to reach out to our stakeholders. In terms of the more detailed aspect of the project, we've got an ambitious numerical simulation plan, going all the way from a very idealized patch simulation in the ocean to understand the key processes, the fine scale processes, and going up to the Earth system model, coupling with the atmosphere. And we also have, in combination, an ambitious fieldwork plan with numerous cruises. And we are actually now about halfway to completion to the project. And we just finished not entirely finished, but almost finished all of fieldwork, which represents a big milestone for the project. So starting really a new phase of the project where we start analyzing all this observation that came up. So I'll stop here. Feel free to engage by email or any means. We really love discussing and collaborating. So thank you very much for your attention, and I hope you the best for the rest of the workshop.
Okay, so big thanks to Jean-Baptiste Sallée. I think we can stop sharing. Okay, perfect. Yeah, so he gave a really nice introduction into the project and the different work packages and what the work is focusing on. And now I would like to call Holly Ayres on the stage to talk a bit more about the Weddell Polynya, which is what Jean-Baptiste also mentioned, that it kind of links to the abrupt events that can play a large role for the Southern Ocean and the heat and carbon uptake.
Brilliant. Thank you, Nadine, for the intro there. So thank you, everyone, for joining us today. I'm going to basically be talking about work package 5, which is all about the Weddell Polynya and the interactions with the global climate. So this is work that I've been doing with David Ferreira at the University of Reading, but also with Milan Orlin, Wanson Park, and Joachim Jelsen at GeoMar in Germany. So a little bit of information about the Polynya, starting with the basics. So a Polynya is an opening in the sea ice, so a small region of sea ice loss with similar ocean air fluxes to large-scale sea ice loss. But in this case, it's enhanced with a region of deep, warm water upwelling to the surface, so formed primarily from deep convection over the Montereys, amongst a mix of sort of other ocean and atmospheric mechanisms that have been discussed in the literature recently. So the Weddell Polynya has only been observed twice in satellite history, once in the 1970s and again in 2016, 2017, not to be confused with the Montereys Polynya, which Aditya will talk a little bit in more detail about later. So most studies out there focus on what causes the Polynya, both atmosphere and ocean. So we're interested on the Polynya's impact on the local and global climate. So the role of the Polynia, so atmospheric circulation, which is the generally large-scale focus of our work package. So it largely focuses on the atmosphere today. It's primarily a window in the ice, so a region of heat and carbon transport between the ocean and the atmosphere, which, according to early research, could have impacts on the local and even global atmospheric circulation. So what are the objectives of work package 5 here? So the first is that the atmospheric response is kind of the main thing we're looking at, so regionally and globally, and the emergence of the Polynia in the Weddell sector. We're also looking at the source of bias in representation of Polynia in dynamics and models, so both in our own models that we run and in Primavera models, so a large CMIT-6 ensemble. The effects of ocean atmosphere feedback on the Polynia and the representation of Polynia dynamics in models, so especially, again, resolution dependence there. How is this different to work that has been done before? So firstly, a lot of atmospheric research, mostly assessing the cause. The previous research is mostly assessing the cause, not the response. So we're looking at the response. We're doing a high and low resolution comparison, lots of models, and the only other study that's previously looked at something similar was limited to one model, so that was a good start for us. Our coupled model will be the first to create a Polynia in both the ocean and atmosphere. And as I say, we'll also have this Primavera analysis of how the model resolution controls the forming of the Polynia and the ocean atmospheric interactions with the Polynia. So for the most part of this talk, I will briefly talk about our Agcm model setup, and that's work that I've been doing here in Reading. Everything else is still very much a work in progress, so this is where we're having our first results and hopefully a published paper in the next couple of months. So this is our Agcm experiment, and so this is a first order response, but also focusing on the difference in model resolution and the different models. So we have run low and high resolution simulations using our free models. So our own mini MIP, we've had Agcm free, Ekman 5, and OpenIFS. And for Agcm and OpenIFS, these were the extremes in the resolution, so the very high resolution and close to 100 kilometer resolution versions of the model. And for the low resolution models, we run them for 100 members, and the high resolution we run with 30. High resolution, as I say, they're very high, so very computationally expensive to run. So where we would like to run more, unfortunately, we can't. So these are forced with sea ice and SSTs from 1974 Polynia, which, although is less likely in future scenarios, it provides a strong and maximum forcing to work with. So the response to the Polynia and the figures I will show from this point onward is calculated as the 1974 Polynia condition scenario minus a massed non-Polynia control over the region. So using the averages of 1980s to 2015 data, where there were no Polynia. So as you can see, there's a nice clear Polynia forcing. So this is the easy part. So these results that I'm going to show you are mostly low resolution, as we haven't quite finished all the high resolution models yet. So these are for August to November, so Polynia months, going across the screen, and Agcm, Ekman, and OpenIFS going down the screen with hatching marking the significant region. And this is positive in the ocean to atmosphere direction. So the first thing to notice is the locality of the response, which all seem fairly similar, with the only differences in kind of shape, and then they will decrease in magnitude as we go into the austral summer. There are only small differences at this point, so notably that Agcm reduces a little bit quicker than the other models, and OpenIFS has a slightly larger response, which is expected to be due to differences in interpolating to different model grids, and also possibly some differences between model time steps, already some interesting differences between how models deal with the Polynia here. Onto surface temperature. So turbulent heat flux is what creates a response in the atmosphere, so ocean to atmosphere. we get the surface temperature, which correlates to the heat flux. They follow the same trends and are locally confined. However, temperature does also increase in the region surrounding the Polynia and to the north and east, downwind of the warming, but this is confined to the region. Precipitation, so that follows a similar pattern, so with similar differences in Agcm and OpenIFS, but notably the region the region of significance is even smaller, and we start to see a lot more noise going on here in the background. So, however, going into sea level pressure, we get something, but it is not significant anymore. But I wanted to show this anyway, because there's clearly something happening. So potentially, this is why I mentioned about having more members. It would be nice to be able to run more members in the low resolution, but in the high resolution, we may face a few difficulties there. So in OpenIFS, we do find a significant response in the meridional wind, and that's associated with this pressure change in September. So that's something, despite there being a lot of noise. So lots of interesting results there just by looking at the low resolution atmosphere only models. We also have the zone mean temperature response aloft, so above the Polynia, Agcm, Ekman, and OpenIFS going across the screen, and all of these show a similar response between each other. So these are confined to the lower troposphere, but with a small significant response aloft, which I call a warming bubble with a chimney. So finally, on the Agcm, we have a quick comparison for the resolution. So with Agcm, the timing and spatial extent is very similar, but the magnitude nearly doubles with resolution. And this is surprising, considering recent studies have shown that resolution doesn't matter that much, and everything seems to be looking similar. So we're currently investigating this, but this is an interesting response, we think. So on to the next piece of the work package, which is by our colleagues at GeoMar, specifically Melin. She's been working very hard on this, and she's working on the Polynia perturbation in a coupled high-resolution nested sweep model. So the nest is the orange box here, and this has a lot of challenges where getting the right forcing is crucial to the atmosphere and ocean response. So I'll just show some preliminary results here, but I'll also demonstrate some challenges. So these are some initial results, and we have the control and nested sweep biases and differences. And before we look at them, I should say that the sea ice is still not quite there. So the ice loss includes the Weddell and then a bit into the Indian Ocean, and also something going on around the Amundsen Sea low. So that's our first challenge. And as I say, it's very hard to get this forcing in a coupled model. So this is the surface temperature along the top, where we see a large significant warming over the Weddell Sea, followed by precipitation below, and there is potentially something in the tropical Atlantic precipitation of interest over here that's significant. There's a decrease there. And again, there's a reduction in pressure, but not significant over the Polynia, which is becoming a bit of a running joke in our team, because it's obviously crucial to forcing. But obviously something we see in all models, even if it's not significant. So potentially some exciting results once we have these finalized here. Finally, I'll just go on to the final part of our work package, which is this Primavera data analysis. So Primavera is basically a large GeoMx ensemble with this forcing. So you have this control 1950s experiment, a historic experiment, and future projections experiment, which is consistent with our 1950s coupled forcing. And these are basically to assess the formation of the Polynia in these models, the ocean atmosphere processes associated with the Polynia, and the climate response to the Polynia. So across the full Primavera data set, comparing different resolutions of atmosphere and ocean. So I think we'll learn a lot from this here. Ooh. Okay, so just here we have the, so this isn't really a result, but from what we know that a low resolution model will probably not really show us much for the Polynia. So there's probably some processes there. A medium, I can't quite get that to work, but that's fine. There we go. A medium resolution model might show us some Polynias. So this is for September here, and we had got a couple of Polynias over a full data set, whereas a higher resolution, see if I can get that to work there. Yeah, a high resolution model may show us a lot more Polynias, and there might be some interesting things going on there. So that's kind of the general idea behind the Primavera analysis. So just a quick summary, so some take-home messages from our research. So models are consistent-ish across similar resolutions for temperature and precipitation in our Agcm experiments, but only in September. And resolutions and models, we do find differences between them and similarities. So that's going to be even more interesting as we analyze it further. Other studies that show potentially large dynamics may rely on secondary feedback. So as I mentioned before, the Agcm experiments, we are not really everything's quite local, but with the coupled model, we may see something that's a little bit further spread. So our work that we're currently doing is where resolutions behave differently, the coupled model, and the Primavera analysis of the Polynia. Thank you very much.
Thank you, Holly, for this nice overview over all the great work that has been done in that work package. And yeah, it's exciting to see that there's quite some work going on and in progress. Yeah, for everyone with us in this session, so please keep your questions, type them in the chat or keep them for later. You will be able to raise your hand and ask questions in the discussion round. And then next, we'll have Shenjie Zhou talking about the Southern Ocean in terms of carbon and heat, and yeah, what we know about carbon and heat in the Southern Ocean.
Sorry, thank you, Nadine. Can you see my slides?
Yes, perfect.
Okay, thank you. Thanks, Nadine. Thanks for having these nice discussion panel session on the SO-CHIC projects. And thanks for having me here presenting some of the work has been done under the SO-CHIC project. I think I will just follow up some of the previous talk, especially JB's project summary, and go into a little bit detail of the SO-CHIC and what each work package is working at. Of course, Holly already gave a nice presentation on the work package 5. And in this talk, there will be a very brief summary of what has been achieved, but of course, more will be covered by following speakers on the most up-to-date progress. So as introduced by JB, the SO-CHIC is designed to look at problems associated with Southern Ocean carbon heat uptake and its impact on the climate. So the reason we are interested in the Southern Ocean, as many of you are aware of, is that the Southern Ocean is actually the real powerhouse of the global circulation, as shown by this nice map, where the Southern Ocean is at the center of the global general ocean circulation. So it is a key site globally where the old deep water rises to the surface, as shown by these blue arrows into the red arrows. And these old and deep waters rises to the surface and thus able to interact with the atmosphere and the cryosphere. So during these processes, large amounts of the heat and carbon are exchanged at the surface in the Southern Ocean, and then sent back to the ocean interior by the circulation system. And in total, in the Southern Ocean, it takes up significant amount of excess heat, which is about 70%, and 40% of anthropogenic carbon dioxide, while the Southern Ocean itself only takes up about 30% of the global ocean surface area. And I think these numbers really highlight the disproportionate importance of the Southern Ocean in regulating the global climate. So the key process that makes the ocean so important in terms of its magnitude of the heat and carbon uptake is the ventilation. So the ventilation of ocean means that the density surface of the ocean outcrops at the surface, which provide a pathway between the surface and deep ocean. And along these pathways, the water and the tracers can move up and down freely. So the tracers including things like heat and carbon. So this pathway in Southern Ocean is highlighted by this oxygen distribution map, where the orange color stands for a older water mass with lower oxygen concentration, and the purple color means the water that recently contacted with the atmosphere and characterized with higher oxygen concentration. So in the Southern Ocean, the deep water is upwelled through the surface wind forcing, and the water from beneath is cold and unsaturated with respect to the anthropogenic carbon, and therefore takes up the heat and carbon from the atmosphere. And then it is sequestering these heat and carbon by the subduction as it moves south, as it moves north. And in total, in global, there is over 70% of the global ocean interior is upwelled and make their last contact with the atmosphere in the Southern Ocean area. So although we know that the Southern Ocean is important for the climate, it is still one of the regions that we know the least in terms of how these processes work together to bring down the heat and carbon and how they change throughout the time. This is evident shown by these large uncertainties of the simulated heat and carbon uptake in the Southern Ocean across our climate models accumulated over the course of last century, which really limited our ability to look into the future of the Southern Ocean with confidence. And one of the main reasons that blocked our understanding and the better constraints of the model in the Southern Ocean is that exact rate at which the ocean ventilates in the Southern Ocean. And this is so far lack of consensus due to limited observations. Yeah, so the SO-CHIC project is trying to answer the questions, or at least trying to advance the community's ability to answer the questions, which is at what rate ocean ventilates in the Southern Ocean. As JB mentioned early on, there are two main conventional pathways for the ocean ventilation in the Southern Ocean. One of them is actually through the entrainment of the water from the underneath across the mixed layer base, which is what we call the upper ocean ventilation. The work package 1 and 2 are designed to understand what processes control the surface fluxes and the mixed layer dynamics that are pivotal for the upper ocean ventilation pathways. And another one is the deep ocean ventilation pathway, which essentially involve the formation of the bottom water through the sea ice freezing and the brine rejection on the Antarctic continental shelves. So the bottom water, it will fill the global abyssal ocean through the general circulation systems, and it's spreading over the global ocean through the circulation, and the mixing with other water masses are actually key for the sequestration of heat and carbon. And the work package 3 in SO-CHIC is aimed to look at what is happening on these pathways. And the final key element, which has been talked about by Holly, is this abrupt shortcut event, which involves the opening of large open ocean Polynia and a deep convection that might bridge deep and the surface ocean over a narrower horizontal extent. And the work package 5 and work package 6 will be then looking at the large scale impact of these localized events on the atmosphere and the overall heat and carbon storage. So what is happening in the Southern Ocean ventilation? I think here I'm just going to briefly showing some of the results that have been achieved under these work packages and talk briefly through what each packages are looking at. There might be some repetition with JB's slides, but hopefully it will give us a better idea of what we're doing here with the SO-CHIC project. So for the work package 1 and 2, looking at the surface fluxes and the upper ocean open ventilation, on the transient scales, it is found that there's a strong storm that are ubiquitous in the Southern Ocean can really be the key for the carbon outgassing by its influence on the mixed layer depths. So the strong wind-driven mixing can essentially brings the carbon-rich water from the mixed layer, below the mixed layer, upwards and affects the surface carbon partial pressure, and eventually the rate of the carbon flux at the surface. And on the long time scales, it is found that the Southern Ocean undergoes a 8% per decade increase in the surface stratification, shown by this red color, over the summertime, mostly driven by these freshwater inputs. And of course, there are a whole suite of other mesoscale processes that control the upper ocean dynamics in the Southern Ocean, which requires more directly measurements in the field with specific design instruments. And I think this part will be covered by Natasha and Marcel later on about the instruments and these novel observation platforms and the results coming out of those measurements. So the work package 3, which is a work package that I'm currently working on, focusing on the deep ocean ventilation associated with the dense bottom water formation, mixing and exports. As part of the work package 3 objectives, we investigate the driver of a long-term bottom water volume reduction in the Weddell Sea. So on the left is the bottom water mass area along the 3 steady transactions in the Weddell Sea basin. So all these time series reveal distinct decline on Weddell Sea bottom water volume, and by over 20% over the past 30 years, average across all these lines. And because that in the Weddell Sea water column, there is a warm saline circumpolar deep water sits on top of the fresher and colder Weddell Sea deep water and bottom water. Therefore, the deepening of the isopycnal caused by the loss of the bottom water volume can actually lead to a warming and a acidification of the water column. So on the right, we are showing the evidence of that. So basically, we're showing the total warming rate of the Weddell Sea water column in white, and we decompose it into the isopycnal displacement in red and the along isopycnal changes in blue. And we found that these isopycnal displacement components can effectively explain all the warming signal deeper than 2,000 meters, with a warming rate of 2 milligray per year. This is equivalent to a warming rate of 0.34 watt meter square, which is 5 times greater than the global average. So what is causing these bottom water volume reduction? And we believe it is a sea ice. So here on the left, we're showing the linear trend of winter sea ice formation rates estimated using this bulk formula. And the linear trend is derived over the period between 1900 to 2020. And we can see there's a pronounced sea ice formation rate decline in front of Ronnie and the Berkner Bank. And these 2 sites are known as the hotspots for the high sea shelf water formation, because that this region has persistent climatic offshore wind that blows away the sea ice and maintain the open of the coastal Polynia, through which the ocean and atmosphere has direct contact and facilitate these heat loss for the sea ice formation. But at the meantime, if we look at the area on the map, which are actually the surface wind trend vector, it actually shows that on the past 30 years, the Weddell Sea continental shelf experiences an inshore or northerly wind trend, suggesting that there's a slowing down of the offshore wind that is climatologically dominating this region. And therefore, we're expecting less expanded coastal Polynia, and therefore less sea ice formation through the Polynia. So on the right, we show a similar results, but with a more focus on the internal sea ice pack on the continental shelf. So the time series show the integrated term of the sea ice body analysis, as indicated by this equation, over these green box on the continental shelf. So the positive value means the sea ice sink, the sea ice source, sorry, and the negative value means the sea ice sink. And the red and blue are the dynamic sea ice flux and the thermodynamic ice growth. So the sum of these two are the sea ice concentration tendency, which is near 0 because of a heavy sea ice coverage over the winter time in this area. So as we can see that these red lines, which stands for the dynamic sea ice flux, it increases over time. Therefore, it became less of a sea ice sink, which is actually correlated very well with these more convergent surface wind forcing, as shown by these gray lines. And as a result, to compensate that, the thermodynamic ice growth decreases, which means there's a less of this, which means these terms became less of a sea ice source as a result of the surface forcing and the sea ice flux. And we believe that these changes of CS can quantitatively explain the observed bottom water volume reduction. And it is also a response of this long-term trend in the large-scale atmospheric circulation associated with the MSNC-low system. And finally, the work package 4.5 and 4.6 are looking at specifically the Weddell Polynya as another major component of the SO-CHIC. So the Polynya has been recently opened up in the Montereys in 2017 and also 2021 since the early 1970s. And given the climatological condition, the opening of these open ocean Polynya can sustain hundreds of watts per meter square heat and tens of millimeters per day fresh water flux to the atmosphere. And these numbers are already also backed up by some of the results shown by Holly in the previous talk. And these in these work packages, Holly and colleagues will be looking at the impact of this opening Polynya on the atmosphere circulation. So just to summarize, what I've showed in all these results suggest that these localized and small-scale processes can have widespread impact on the Southern Ocean ventilation and therefore influence its heat and carbon uptake and storage. And we believe that it requires the continuous measurements or observation of the key sites of these events in order to better understand them, and therefore to better constrain our climate models using the understanding. And finally, hopefully, can level up our confidence of looking to the future of the Southern Ocean status. Thank you.
Thank you, Shenjie, for this great overview of the different ventilation pathways in the Southern Ocean. And yeah, also the ventilation on different timescales. Yeah, so now we're gonna move on to Aditya, who will talk about the Montereys Polynya and a bit more in detail about work package 4.
Hello, everyone. Sorry about I have a bit of a bad throat. So I'm going to be representing work package 4, and our work is more focused on the Montereys. And I'll be talking today about the preconditioning in the ocean that led to the formation of the Montereys Polynya. So work package 4 has Fabien Roquet, Berta Gilk at the University of Gothenburg, and Alberto Carabato from the University of Southampton. So to set up the region, we are looking at the Weddell Sea. The Montereys is a sea mound located close to the prime meridian. It's at the shallowest, it can get as shallow as about 1,000 meters. And an important thing to note is that the Weddell Gyre, the lower arm of the Weddell Gyre flows past the Montereys. So I will be talking about the implications of the interaction between flow with topography around the Montereys. So I won't spend much time about this. Polynyas are important because they can expose the ocean, the underlying ocean, and the heat stored within the ocean to the atmosphere during winter. And you can have enormous storage of heat in the ocean, especially if the circumpolar deep water layer, which is considered warm, a warm water layer in the Southern Ocean with temperatures of about 2 degrees. If this layer is somehow able to be connected to the surface waters, it can then lead to a huge amount of heat flux to the atmosphere, and it can set up vertical convection. So the Montereys Polynya is considered to be a precursor to the much larger Weddell Polynya that opened up in the 70s. And the Polynya that we saw in 2017 was once again initiated over the Montereys Polynya and remained much smaller in size than what we saw in the 1970s. So some of the questions that we ask here is what are the processes controlling the formation and persistence of the Polynia, and we look more specifically at the role of the interaction between the flow with topography. So most of the results I show here are from the Southern Ocean State Estimate. It's an estimate produced by assimilating available observations and using a least squares method to fit the numerical model output to the observations. But the data assimilation does not distort the budgets of the conservative fields in the ocean, so it remains physically consistent. So the mixed layer in the years leading up to the Polynia in 2017 became progressively more salty. And this is again reported widely in the literature, and we also see it from floats in the region. The white arrows you see here are the geostrophic velocity. And you notice that on the northern flank and on the southern flank, you have this westward flowing arm, which is the Weddell Gyre. Right, so we know that this, the surface became saltier, which weakened the stratification and allowed vertical mixing between the mixed layer and the circumpolar deep water layer that's quite shallow in these regions, and it exists almost just below the pycnocline. And it's the circumpolar deep water layer that ultimately supplies heat to the surface to keep the Polynia open. So we know that that this is a key element. The increasing salt at the surface is a key element in weakening the stratification. So now let's look at the salinity budget averaged over the entire region, and you can see that the black line is the salinity of the upper 20 meters. The red line is the component due to surface fluxes, and you see that the seasonality is dominated by surface fluxes. As you would expect, when sea ice grows, you get more salt, and when sea ice melts, you get reduction in salinity. And across the years, you see that the vertical diffusion contributed to increasing the salinity, along with horizontal advection. Now, the vertical diffusion, again, is a key element here because you need the salt from the underlying circumpolar deep water layer, which is warmer and saltier, to be injected up into the mixed layer to push the surface towards a saltier regime and ultimately weakening the stratification. So that's the same picture you see here on these maps. This is the vertical diffusion and the surface salinity flux, time integrated from March through September, the period during which the surface becomes saltier, the sea ice growth period. And you notice that the vertical diffusion primarily is adding salt in this region surrounding Montereys, which has been referred to as the halo region in the literature. And this is a region where the circumpolar deep water layer also shoals to a much shallower depth. So you would sort of expect this to happen here. And of course, the surface salinity during the non-Polynia years is adding salt because of the formation of sea ice. And during the Polynia years, you see the effect of melting, sort of reducing salinity in the surface layer. Now, finally, we asked this question: why did the Polynia initiate over the northern flank of the Montereys in 2017? You notice here that the sea ice concentration begins weakening over the northern flank. So that's about, the isopaths here are 3,000, 4,000, and 5,000 meters. And you notice that the initial weakening, this is from the remotely sensed sea ice concentration of NSIDC, and the red contour lines are from the Southern Ocean State Estimate, which is also broadly consistent. It shows an initial weakening over the northern flank. To do this, we rely on potential vorticity budgets. Why potential vorticity? Because PV represents the stratification. It's a tracer that's conserved along isopycnals, and it's primarily affected by surface stresses and diabatic fluxes. So if we looked at budgets of PV, we can then retrieve the main drivers of the water column stratification. And our focus will be on the frictional cross-frontal term, which is mainly driven by Ekman cross-frontal transport. So if you have, in this illustration, you see a top view of denser waters and lighter waters. You have a front here. And if you have winds that blow down the front, you can have, so in the southern hemisphere, Ekman transport is to the left, and you get denser waters being pushed over lighter waters, resulting in weakening of the stratification, leading to vertical instability. So our focus is going to be on the frictional term, referred to here as JF. This is just to show you that across the years, leading up to the Polynia, the water column becomes progressively weaker and weaker in stratification, represented here by weakening of PV. And finally, we look at the frictional term here. In the maps here, you notice that in the years leading up to the Polynia, you see these blue-colored regions, which indicates that the frictional term is strengthening PV. So negative here implies stronger PV. PV is negative in the southern hemisphere, and in the years 2016 and 17, the blue area sort of weakens, and the red regions start moving poleward closer to the Montereys Taylor column. And you see something similar when you average over just the northern flank, and you see the inset map here showing the region selected as the northern flank. And when you average over the northern flank, again, the black line here represents total PV, always negative. It gets weaker during winter and stronger again during summer. So that is the seasonal cycle you see here. And the blue term is our frictional term. And you notice that in the years leading up to, in the years 2013 through parts of 2015, the slope is more or less negative during the sea ice growth period, and it leads to a strengthening of PV. Whereas sometime around May or June of 2015, this flips, and you notice that the frictional term is actually acting to weaken the stratification, and the blue arrows sort of represent that change in that slope. And so I said earlier that the frictional term is primarily driven by the Ekman transport. So let's look at the Ekman transport of salinity, and you notice that once again, the spatial patterns that we noticed in the frictional term is sort of repeated here. You once again notice that the regions that were blue here, indicating a removal of salinity, sort of weaken and disappear in 2017, and the red areas move southward closer to the Montereys Taylor column, indicating that horizontal Ekman transport of salinity across the front is injecting salt into this region, the northern flank, and it's providing the sort of additional kick to the water column to weaken it, and it acts in concert with the other term, which is the vertical injection of salinity from the circumpolar deep water layer. And what caused this? We show the ocean surface stresses, and we show that in fact the stresses become stronger. They sort of move poleward towards the Taylor column, and if you notice the arrows that show the stress anomaly, the arrows too sort of change their direction and become oriented in the downfront direction, which promotes the Ekman transport across the front, ultimately leading to the water column weakening sufficiently to initiate the Polynia over the northern flank. And finally, I'll end with Berta Gould's work, which is high-resolution modeling of the Montereys region. I'll just share some initial results. The questions that she's trying to answer are, once again, to sort of run sensitivity tests over a much longer period of running a numerical model, which is based on NEMO, and she's going to be focusing on the Taylor column and the halo around the Taylor column. And here are some initial results from that. These are results from a 1/12 degree resolution, and you notice that the model is able to represent the Taylor column around, the warm halo around the Taylor column in the Montereys region. And the work that she's currently pursuing is to carry out sensitivity runs to identify external sources of forcing that could lead to the vertical mixing and convective instabilities. I'll stop with that. Thank you.
Thank you very much, Aditya, for this very detailed insight on the ocean side of the formation of the open ocean Polynia. So to all the listeners, please keep all your questions to after we are done with the presentations, and then we'll have some time for that. And next on is Natasha Lucas, who will talk about some more observations from gliders, which is linked to the work package 2 of the project.
Sorry, some noise would help, right? Can you see the right screen? Because I can't seem to
we see
which screen you're looking at.
We see your, I think you're sharing the whole screen. So there is the presentation in the background, but we don't see it in full screen.
Okay. How's that? Better?
Yeah, great. Perfect.
Amazing. Great. I'll just start my timer. So hello, everybody, and welcome. Thank you very much, particularly to Shenjie and Aditya, for introducing exactly what I'm going to talk about here, which is transient storms, stratification, downfront winds, submesoscale instabilities, basically the small scale effects that link in with the larger scale processes. I'm speaking on behalf of British Antarctic Survey under the umbrella of UKRI, which is one of the consortium partners that you can see here for SO-CHIC. And I'm going to talk about ocean gliders generally and how they fit into work package 2. That didn't work. Here we go. Amazing. So what I'm going to talk about is what is work package 2 and what its research goals. I'm then going to look at some previous work that I've done looking at gliders and understanding the ocean surface boundary layer and how that fits in with the greater context of SO-CHIC and work package 2, and then I'm going to finish with some of our current findings of our ocean gliders in the water at the moment. So to get going, SO-CHIC work package 2 and its research goals. Basically, what SO-CHIC work package 2 is looking at, as has been illustrated before, is that surface of the ocean. We're looking at the surface down to around 1,000 meters, which includes the ocean surface boundary layer and the water below. And what we're looking at is how the properties and the mechanisms within this layer control the evolution of that layer, which affects the fluxing between the ocean surface and the atmosphere and the ocean surface and the deeper interior. And we're trying to understand and be able to pick apart and quantify different mechanisms that affect the properties of this layer, which will obviously affect the fluxes. So whether Ekman buoyancy forcing or convective buoyancy forcing is more important, or submesoscale independent instabilities, or rather less of the importance, but how of all of these different flavors of mechanisms within the ocean affect and how we can quantify them to be able to understand this subduction of heat and carbon through the mixed layer from the atmosphere and into the deeper ocean. Work package 2 finishes with using these observational outputs of the ocean gliders to be able to test parameterizations to understand the differences between Langmuir circulation and submesoscale, which I will mention in this talk. So previous work and how this fits in with the larger context. My work previous to this was working with Bangor University, where we were looking at quantifying the ocean surface boundary layer as part of the osmosis project, which was directly linked to this ocean surface boundary layer. And what we did was we deployed an ocean glider that was able to measure TKE dissipation, which from here on in I'll just call dissipation, but basically it's a proxy for ocean mixing, so a small scale process that affects all of the larger scale processes. With this ocean glider, we always have a CTD, and some ocean gliders have different measurements for ecological parameters. The main thing with this study was that we were able to measure in an autumn storm. Now, this is a real step change. Gliders are a step change in being able to get the information. Before, we weren't able to measure turbulent kinetic energy dissipation during storms because the instruments had to be deployed from the back of ships. So therefore, if you're in high seas, you're not allowed to take these measurements. And obviously, storms are very important for mixing. So it's kind of a conundrum with ocean measurements, and the ocean gliders are filling that gap. This work, what we did was we were able to look at observations and fit them with an LES, which is large eddy simulation model. So a small scale model that incorporated Langmuir, which is the wave effect. We improved our understanding of the momentum balance and shear within the water column. We predicted the rate of mixed layer deepening, heat budget, dissipation, and inertial currents in the ocean surface boundary layer, but it left questions. So the results from this model. On the top right here, what you have is the location. So the main point here, the main take home is this is in the Atlantic, not in the Southern Ocean. So the stratification is affected by, influenced by temperature alone. We can kind of throw salinity out here. The top left, what you have is the main take home. So at the top panel, you've got wind and wave, black being the friction velocity and blue being the Stokes drift. Below that, you have the buoyancy flux into and out of the surface, which is also emphasized by these vertical red lines, which are the sunrise and sunset, and the air pressure. Below that, we have the temperature within the water column, the top 100 meters by time, with temperature being the color. And below that, we have the take home, the money shot, let's call it, which is the dissipation in the water column. And so what is the main things to pull out here? So first of all, at the beginning of the time series, before the green lines, the green vertical lines, which is the storm period, the beginning of the time periods, it's fairly quiescent, not much wind and wave. I pull your attention particularly to the daytime of 262 in the bottom panel, where you can see the dissipation is encapsulated within a very weakly stratified surface layer because the heat is stabilizing the surface and causing this weakly stratified layer. And then at nighttime in this diurnal cycle, you can see that you get convective cooling at the surface. And so you get a buoyancy flux increasing the dissipation. It's beautiful. And then later on, you can really see between the green panels where the dissipation, the energy in the water column is increasing and being transferred down through the water column during the storm. And again, I emphasize this wasn't able to be measured previous to us having ocean microstructure gliders. So in the two panels here, you've got the blue box and the orange box, which are represented in the bottom right-hand side. The blue is as the storm's building, and the orange is when the storm is in full flow. So let's take this down to the bottom right-hand side now. The black dots are the sum of, so the representation of all the dissipation from the glider, but we're scaling this by what's known as a Langmuir velocity scale, shown on the left-hand side in the equation. And it's the same as a friction velocity, but it also incorporates a Stokes drift. So it incorporates a wave term, which allows us to look at the vortex pull down of Langmuir velocity. You can see the cyan line, which is the geometric mean of these dissipation profiles. And the dark blue line is the large eddy simulation of dissipation from this Langmuir model. And the take home here is that we're able to model the ocean boundary surface depth, the heating, the changes, but with the model with Langmuir and without, the difference in that ocean boundary layer depth change is small. So being able to conclude whether this Langmuir model, which does appear to fit, but how can we really say that it's not the shear model with no wave terms to be able to fit our understanding of how these dynamics change? We need a longer storm with a longer duration. And what better for that than the Southern Ocean, where you have big storms for a very long period of time? SO-CHIC. Moreover, what else were we not able to pick apart with this study? And what you can see is the site here at the top left panel. The green and red is the path of the microstructure glider. And the red in particular is as it's going into the storm period. And you can see that it's rotating. Now, this rotation of the glider is at the inertial period for the area, pretty much, give or take. And so on the bottom right-hand panel here, you've got the temperature by the glider in the crosses and the temperature modeled with the large edge simulation in the cyan line. And you can see that the large edge simulation is able to represent the mixed layer deepening, but that there is a lot of texture, a lot of depth and information available in the temperature that is not seen in the model as a representation as it is. And we believe this is temperature and salinity changes and mixing changes due to sub-mesoscale instabilities that wasn't able to be quantified in this study. And if it's rotating, it may well be rotating into and out of or across a front. So being able to pick this information apart is important. And so we move on to SO-CHIC. So SO-CHIC is going to give us the chance to use these ocean microstructure gliders. The top left panel here is Marcel and Seb's, really, I recommend you visit it, site called Rome Marginal Ice Zone. And up there, you've got the wind stress, and you can just about see the location of our gliders here. The bottom right is just Null School, where we've got the red star is the location of our study site, the gliders. And we have the currents in color and the wind in overlay. The point is there's a lot going on and a lot of storms for us to be able to quantify these changes. So let's finish with some actual results that we've got so far. I mean, there is a lot to unpick now. These are preliminary. On the left-hand side here, we have black, red, and cyan. The cyan, unfortunately, is our ocean microstructure glider that measures turbulence, which I am very sad to say has died and is now somewhere in the bottom of the ocean, or maybe to be washed up in Australia in the future. The black is Marcel's sea glider that's just been taken out, and you can see its transect and where it's been doing a sub-mesoscale bow tie. And to finish, I'll just draw your attention to the red. Sorry, I'm a little bit behind on time. We started on the 15th. On the 24th of March to the 24th of May, we started this sub-mesoscale bow tie pattern. We then moved north across the southern boundary from the 3rd to the 6th of June. And then up on the 19th of June, we started a mesoscale transect of 111 kilometers north-south. And then after a brief calibration on the 15th of July, from the 18th until the present, we've been doing sub-mesoscale bow ties. And if we break down the data set that we've got on the bottom right-hand side here into these regions, I suppose the main take-home points here with respect to time is that, first of all, the sub-mesoscale bow tie over 2 months, you can see the surface layer is cooling as we're going from autumn into winter. The winter layer is deepening and becoming smaller. You can clearly see the changes across the southern boundary, which is super interesting here in temperature and salinity, the panels here. On the left-hand side here, and at the top, we have a color scale, dark blue to green, which is the changes in salinity and temperature over time. And on the little panels here, you can see those changes by depth. And so you can clearly see the mesoscale transect. There's a lot of interesting information going on in the surface mixed layer here in both temperature and salinity. And finally, in the sub-mesoscale bow tie, you can see the surface waters cooling as we're getting further and further into the time series. So I'm going to have to move on, I'm afraid, but we have some biological results here: chlorophyll, scatter, and photosynthetically activated radiation. So to finish off, gliders are a step change in long-term information about the ocean that we haven't been able to measure before. We can explain the ocean surface boundary layer in a one-dimensional framework, which is why we've been able to explain it for so long. But we are missing all of these three-dimensional sub-mesoscale processes that are important for the temperature and salinity in the surface, which is important for the air sea fluxes. So we cannot fully quantify until we're able to spread out to a larger scale. We hope to unpick this with SO-CHIC, looking at these storms, mesoscale variability and seasonal changes. And so far, gliders have been successful with an exclamation mark. There have been some losses, but we've been out 5 months and we're planned for 9, which is going to be a world's first unprecedented data set. Thanks for your time.
Thank you very much, Natasha. That was nice to see some results from the gliders, and also to have some results from outside the Southern Ocean as a comparison. And yeah, with that, we're gonna move over to the last talk by Marcel about the SO-CHIC cruise and more observations and how SO-CHIC will fill the gaps.
Can you see full screen?
Yes,
Yeah,
perfect.
cool. Thanks. Yeah, so I mean, the first thing I want to say is thank you to all the previous speakers. You guys have provided a really nice overview, motivation for why we're trying to understand these regions, and really shown how I think the modeling community has driven a lot of the ideas and sort of the hypotheses around these regions, and given us a lot of fuel to try and use our observations to understand these places better. So as you know, SO-CHIC is both an observational and a modeling experiment, and I'm going to talk about some of the observations that we've been doing, or at least that we are continually doing and that we have done as a part of the SO-CHIC expedition, which was a cruise that was done in the beginning of this year. And before I get into the cruise, trying to give you an overview of why we went on this cruise in the first place. And there are 2 main objectives that we tried to achieve. And the first was to provide a very high resolution mapping of the Montereys region, to give us some sort of progress in our understanding of the Polynia, and use it as a basis which we can compare some of the modeling results to as well. The second part of the cruise hasn't really been spoken about much yet, and this was to try and understand a region further north of the Montereys in the Weddell Sea, and this is a region of CO2 outgassing in the Southern Ocean. And this region, because it's the Southern Ocean and observations are so rare there, it's a region that hasn't really been understood much in the past. And so our idea here is to try and map these regions more, and Tasha's given us a really nice overview as to some of the results that have come out of this already, and I'll show you sort of what was done there and some other work that was also done as a part of this experiment. And yeah, so the data analysis, of course, is lots going on at the moment, and a lot of stuff happening in the individual work packages, but it's still ongoing and there's still so much more that needs to be done. So what did we do? So there was 17 scientific personnel as a part of the SO-CHIC cruise, and we had 11 days to do our work in the Southern Ocean. And we went on the South African polar research ship, the SA Agulhas 2, which I must say is an impressive research vessel, and gave us really a wonderful platform to be able to conduct our research, and use this opportunity to say that the ship's crew and captain did an absolutely fantastic job in helping us achieve our objectives. We were out in the Southern Ocean for 11 days, and the ship didn't just go down as a part of the SO-CHIC, but also its annual voyage, which is a logistical voyage to resupply the South African Antarctic research base. And we kind of piggybacked on that and used some of the time to do our work. The first experiment we did was to go and map the Montereys region, as I've said, and this little image gives you an idea of our cruise track and where we went. shown by the red lines here. So we started off at the Antarctic continent, and then went out to the Maud Rise and did 3 transects across the Maud Rise, and then came back to the continent before moving further north to do the rest of the work. And then one little snippet here I'll add is that during this particular season, and as you have learned from the previous talks, the Maud Rise Polynia doesn't happen every single year. It's in fact an extremely rare event, but it turns out that the year we did our observations, there was a Polynia. So that is a really nice sort of, I wouldn't say planned, even though it was written in the proposal that the idea was to study the Polynia. It was a really nice surprise for us and an opportunity to understand the dynamics in an important year. So we did, as I said, we did 3 CTD transects across the region, and here I'm showing you the temperature sections across in these transects, and this section relates to the yellow dots in the map. And what you can see immediately, and this is temperature as I said, what you can see immediately is a strong front between what's within the Maud Rise, the Taylor column within the Maud Rise, and the warm water halo that surrounds the Maud Rise that Aditya spoke about very well. And you can see how sharp that front is. And we see it not only in one section, but we see it in 3 different sections as well. And so it gives us a sort of platform to use these observations to really validate what the models are telling us. But that's not all we did in the Maud Rise region. In fact, we did a lot of other deployments. So beyond the CTDs, we deployed some bio-Auger floats, which are floats that measure not only physical parameters of temperature and salinity, but also biological parameters such as fluorescence, oxygen, and pH. Then there were some SO-CHIC specific instruments that were developed for this project, one of which is called a profiling of the Polynia instrument, or ProPol for short. And this is effectively an Auger float, not any different to the usual ones, except it's tethered to a string that is moored to the sea floor. And the value in this is that it remains sort of at site in the Polynia for its duration of its sampling. And so it follows the normal Auger float sampling plan, except it remains in the Polynia. And this is really nice because it gives you a long-term view of the region that otherwise a float would just drift out of. Then there is another one called the Autonomous System for Auger Float Release, which is, see my cursor, it's this one over here. And this is also a really neat instrument that was deployed. It's a mooring, effectively. It sits on the sea floor. And you can see 4 Auger floats attached to it. And each of these Auger floats are programmed to release at different periods of the year, again, giving you that really nice sort of annual period or annual cycle of upper ocean measurements. And we also deployed some what's called up-tempo buoys, which is temperature buoys that temperature sensors that are attached to a buoy that sample the upper 60 meters of the ocean, and they drift around collecting Lagrangian observations. So we have the Eulerian framework from the moorings and the ProPol, and we also have a Lagrangian perspective from these buoys, and also an upward-looking sonar, which is very useful because it can track the formation and melting of sea ice in the region. And so combining this system of profiling floats, drifting buoys, and sea ice formation and melt, you can get a full picture of exactly what the under ocean, within the ocean, what the development of the TNS properties are in relation to that ice growth and melt. And then finally, we did some autonomous measurements from gliders that Natasha has spoken very well about previously, and what's called a sail buoy, which kind of looks like that little sailboat in the bottom right-hand corner. And this is a very robust instrument. This instrument was actually just picked up as a part of the winter voyage that went down last month. So remained in the ocean for over 6 months, which is quite a feat considering the size of the 1.5 meter size of that instrument, and it uses its wing to navigate its way around the Southern Ocean. so we can control its direction. So some results from this Montereys experiment, and here I'm just showing you from the sail buoy. So this is its path. You can see the contours of the Montereys here, and you can see we did these sort of on-off shelf transects, giving us high resolution information of the temperature salinity, but also the wind speed, air temperature, and surface currents. And the first kind of things that we can notice from this is that there's a lot of variability in the temperature around this region, and there's a lot of change in the small scale currents or the small scale eddies as well. And this might give us some idea as to how the flow between Taylor cap of the Montereys and the warm water ring around the Montereys interacts with each other. Then we can look underneath the ocean as well. And here we did some repeat transects with our diving glider, the sea glider. And one of the things we're starting to look at is not only how sharp that front is in this really high resolution space, but also how the slope of that front can change from one region to the next in the Montereys, and thinking about what are the dynamics that are causing that, and what does that mean for potential exchange of warm water into the Taylor cap, onto the Taylor cap rather. Then we had another region, as I mentioned earlier, which is the subpolar region. This region is very important for Southern Ocean outgassing of carbon dioxide. So as spoken about previously, the Southern Ocean is important for the uptake of oceanic carbon, but it doesn't only take up carbon, it also releases carbon to the atmosphere in this sort of ring around the Southern Ocean. And this ring is formed this way because it's a region where deep waters actually reach the surface of the ocean. So waters that have been in the ocean interior for over 1,000 years are now being outgassed or reaching the surface of the Southern Ocean. And these waters are typically rich in carbon dioxide. And so when they get to the surface, they actually release carbon dioxide because their concentrations larger than that of the atmosphere itself. And so how the modulation of this water reaches the surface and how much carbon gets released is relatively well mapped, except we don't really understand the impact of storms on this process, and we don't really understand the impact of eddies on this process. And how does it change from summer to winter to spring, and what are the mechanisms that create that change? And so one of the objectives here is to put the gliders in the water to measure these processes, as well as other platforms as well. So what we did is we did a few more CTDs in this region, deployed a few more Auger floats as well, and deployed another sea glider, which Natasha has spoken about previously. Another instrument we deployed is called a karaoke buoy, and this is a drifting platform measuring CO2 fluxes, so the carbon concentration of the atmosphere and the ocean itself, to look at that air-sea CO2 exchange and using the diving glider to try and understand what are the interior mechanisms that might be causing that. So a little bit of results from these observations. So here you can see the map of the karaoke buoy drifting in time from west to east. And the color of that map is showing you the chlorophyll concentration. So what we can learn from this is that it's sampling in a region of strong biological growth, and this is the summer time, so we can expect this for this region. And here I show you one event. So this is one particular storm that occurred during this period. And the karaoke buoy measured this very strong oxygen increase associated with a decrease in dissolved inorganic carbon or a carbon drawdown into the ocean. And this oxygen increase gives us the clue as to why carbon is decreasing in this region. It's because there's an increase in the biological growth, as we can see also from the satellite images in the map. And this has led to a supersaturation of oxygen in this region. But then after this increase, you see this really sharp decrease in the oxygen and increase in the carbon concentration as well. And because we know this is a region that carbon comes up to the ocean surface, we looked at the wind speed as measured from the karaoke buoy 2. Notice that this really strong storm passed through, increasing the winds, increasing the dissipation, and mixing up this carbon-rich deep water from below. And so what this first sort of window into these observations has given us is that, over very short time scales in the scale of a storm, we can see these really rapid responses in how the carbon fluxes between the ocean and the atmosphere. And then I'll just close off to say that there is still actually more work that needs to be done. We're only halfway through SO-CHIC. And that is to deploy an ADCP mooring onto the moored rise itself to have further investigation into the currents that exchange water properties between the Taylor Cap and the warm water ring. And then finally, as we speak, there are 2 sail drones that are in the water moving towards the profiling glider that's still there. And this sail drone instrument is a really impressive instrument, and it's considered sort of a Christmas tree of sensors. It's quite large. It's about 5 to 7 meters long, and it contains the full suite of sensors that give you information about the heat flux between the ocean atmosphere as well as the carbon flux. And so this experiment has just began, and we're really excited to see sort of the data that comes out of this. And that's it. Thank you for listening.
Yeah, thank you, Marcel, for this nice overview of all the observations that we have taken during that cruise, and what we can do with these observations. Yeah, so I think now we have seen all the work that has been done so far within the SO-CHIC project, and also all the still open questions that we're trying to answer in the second half of the project, or more questions that we will open. And yeah, I think we've had now we have a nice insight in all the research within the SO-CHIC project, and I think it's time to open the floor for everyone in this session now to answer questions and or add any discussion points. And these questions, they can be directly related to any of the presentations and to any of the speakers, or also more general on Southern Ocean and heat and carbon uptake in the Southern Ocean. Yeah, so please don't be shy and ask questions. Also the speakers, of course, are welcome to ask questions. Yeah, Aditya, you're raising your hand. Please go ahead.
Yeah, I have a question for Shenjie. Shenjie, so you were talking about the reduction of dense shelf water, the reduction in the amount of BSW produced in the Weddell Sea. What time period is this, and do you see, as a result of the reduction in the dense shelf water, do you see any sort of change in the exchanges between shelf waters and circumpolar deep water?
So the first question, the time scale, yeah, the time scale that we're looking at is the multiplicado time scale, which is roughly the time period that we have for the CDD observations, which is roughly about 30 years. So yeah, so the second question, the exchange between the deep water and the circumpolar deep water, we take a look at the water mass area for different water masses observed along the CDD transects. Surprisingly, we didn't really found any change in the Weddell deep water, which sits in between the bottom water and the circumpolar deep water. But there is a increase in terms of the volume of circumpolar deep water. And we think, we hypothesize that it's probably the results of the, a result of the reduction of the bottom water. Therefore, there's more circumpolar deep water entailed into the Weddell Sea gyre as a response to that sort of volume loss at the very bottom of the water column. At the same time, we do see there's a shortening of the circumpolar deep water depth, but the exchange rate of the circumpolar deep water and the dense shelf water on the slope, I think there's very little we can say about that from the observation, because there's not much sustained observation being deployed there on the slope. So yeah.
So I have a follow-up question on that. So the reduction in the volume of the bottom water, you have that from hydrographic profiles, right? And do you have any feeling of whether it also changes the circulation of the bottom water? Like, is there, as it shallows, does it also change how much bottom water is transported northward and distributed further out of the Southern Ocean?
I think, yeah, that's a good question. So from what I understand, the dense water that gets exported out of the Weddell Sea is not actually the bottom water, because the bottom water is too deep, so it can't really go across the northern boundary of the Weddell Sea, which is characterized by the South Scotia Ridge. So what's actually being exported out of the Weddell Sea is actually the Weddell Sea deep water, so which is slightly fresher or slightly lighter than the bottom water. So the change of the bottom water volume will change the critical isopycnal depth, which does, this heaving of isopycnal does change the properties of the exported deep water. So I think the deepening of the isopycnal will lead to a lighter exported deep water out of the Weddell Sea, which is actually being observed in the steady transactions that's been deployed along the A23, which right across the South Scotia Ridge, for the northern part of that transects do see the decreased signal of the exported deep water volume out of the Weddell Sea, accompanied by this decrease of the bottom water within the Weddell Sea basin.
Yeah,
but whether or not that changed the circulation strength, I'm not 100% sure, because we do have the sea surface height measurements, but we didn't really find any good correlation between the bottom water area and the circulation strength in the same period.
Yeah, I guess it might not be enough to just have the sea surface height.
Yeah.
To infer the velocities. Yeah, Marcel, you have a question?
I have a question for Aditya. You showed that one of the main mechanisms for transport of salty water onto the Taylor cap is Ekman advection, right?
Okay. Yeah.
Do you have any idea if it's confined to the surface mix layer, or is there any exchange happening in the interior as well?
Yeah, so it's not just the Ekman, it's also the vertical diffusion from the circumpolar deep water layer. So both of them are acting in concert. But the vertical diffusion acts all around the halo, but the Ekman transport seems to be mostly in the northern flank. But and also the Ekman transport is only in the surface Ekman layer. We didn't see any other lateral advection below the surface layers.
Mm-hmm. And do you think there's any, maybe it's tricky to look at, but any indication of a long isopycnal transport, sort of spiciness that's moving water across?
Yeah, I don't know. Martin Moorman's work comes to my mind, but I don't. I haven't looked at that, and maybe I need a higher resolution model than just 1/6 degrees to talk about that. Yeah.
Mm-hmm. Cool. Thanks.
Yeah, Shenjie, you've got a question as well.
I have a question for Marcel. So I was noticing that toward the end of your presentation, you're showing the storm activities and the increase of the surface carbon concentration. And in that plot, I noticed there's sort of a lag between the increase of the wind speed and the increase of the surface carbon dioxide. I was wondering whether that lag is significant, or is that anything that you expect? Or is there a lag at all?
Yeah. Yeah, I mean, okay, trying to think about this. The lag that we expect, I think, would come because when the wind increases, it doesn't automatically increase the dissipation to beyond the mixed layer depth. I guess it depends on the strength of the wind as well, but some initial observations from a different study from Sarah Nicholson, which showed dissipation in this region and how it changes with storms, shows that, you know, you increase the dissipation within the mixed layer first, and then if a storm can continue for some time, then you can actually reach the end of the mixed layer. And so what our study, what these results are showing initially at least, is that perhaps there's something of similar mechanisms happening, is that the storm is increasing the dissipation, but it's not actually reaching the base of the mixed layer yet. And only after some time or some speed or strength, it actually gets to that base and can start the entrainment process. And I guess it also has to break down that stratification first, to bring up that DIC into the mixed layer. But I mean, we would need to look into this more carefully. But that's my first thoughts.
Thanks.
Sure.
Just to add to that, Marcel, that is also what we found in the Atlantic, in that we're able to see the energy, the dissipation moving down into the water column, but we're seeing the dissipation in the water column and that in the transition layer, which I've found since I've moved into the Southern Ocean has a slightly different definition in the Southern Ocean than the Atlantic. But the transition layer is basically the thermocline, the stratified layer. And the point I'm getting at here is that there's a different pulse response in the surface layer to the transition layer within the Atlantic. Whether that emulates across in other oceans, I would assume it would. But obviously different stratification mechanisms and layers of stratification within deep ocean dynamics in the Weddell Sea. But the point I'm getting at is there are different mechanisms going on. There's different forcings. And until we can really quantify that over, as Marcel says, over a long period of time, the storms, the storms will eat away at the mixed layer. They reduce the mixed layer depth, but the base of the transition layer in the study that I carried out actually remains the same. So this transition layer actually gets smaller. It's getting eaten away, but the stratification within that transition layer weakens, so that the fluxes or the entrainment or the exchange of masses between that deep layer and the surface layer is easier, because that potential energy barrier isn't as strong anymore. And so, with time, with the potential energy barrier is either expanded or eroded, then I think there may be I mean, I don't know, but it would be interesting to see whether that massively affects the fluxes between the deep ocean interior and that surface layer. And particularly when in the data set from SO-CHIC that we've got so far, you can really see the seasonal changes as well, affecting obviously the number of storms that we have, but just the general surface cooling as well.
Yeah, thanks for elaborating on that. And I'm a bit wondering, thinking more in a bigger scale, like SO-CHIC related question. So you see in these observations that those small scale and small scale processes are very important for the ventilation and for the exchange between the mixed layer and the deeper layers. And would you say, and then on the other side, we kind of struggle with capturing the whole Southern Ocean in the models. And would you say that it is indeed the small scale processes that are just really the big problem in the models, or do you think that it's also, I don't know, that it's just a small part of it? Yeah, Natasha.
This really sings to me, and that I suppose it calls back to Wunsch and Monk many years ago. Being Americans, they were like, oh, let's just sort out the big stuff and not sweat the small stuff, and it'll all sort itself out and we'll understand. And it feels, excuse my dreadful accent, but the point is, don't sweat the small stuff is what their quote was. And yet what I feel like is actually we're getting to the point where we really need to not sweat the big stuff and understand the small stuff, because that then, and how that plays out in the bigger scale. So we're kind of flipping it on its head. We're starting to understand these big processes, and this is really the long time series that you can get from models that you cannot get from observations. But the more that these observations are improving and being able to feed, and the more we're working together, which really is a big thing for the last project and for the SO-CHIC project, the more the modelers and the observationalists are talking about how these scales might fit, and what parameters do you need to move up to this scale, and what do we need to observe in order to be able to feed into these models. And so for me, it feels like it's kind of flipping on its head. We now need to sweat the small scales in order to be able to understand which big scales we can use or not use. We've used one-dimensional parameterizations in the loosest sense of the words, but we've looked at friction velocities and surface forcing effects that affect energy and dissipation and mixed layer depth. And we can approximate it with these. We have been doing for, tens of years. But what we're realizing is that all of these nuances in the small scales, such as the different temperature and salinity, which affects these fluxes, which, as we can see from all the presentations, are super important for exchange, are actually all wrapped up in the small scale, the smaller models, the smaller observations, so that we can really build up the layers, I feel.
So you would say that by now we know basically enough about the large scales that the models are able to capture, and then we need to collect more observations and more knowledge with like fine scale models to dive deeper into the small scales and then feed it back again into the bigger models.
Yeah, I suppose I wouldn't go as far to say as we don't need to know about any more of the big scale, because we always need to know more. We have a thirst for knowledge, being human. But yeah, I do feel that now everything seems to be, I mean, maybe it's because you can do what's capable at the time, and the technology is moving on in observations so rapidly that we're able to get so much more out using these gliders. And the other autonomous probes that Marcel's been pointing out, the Caracal boy, the sail drones. I mean, this is a step change in ocean observations, and it's happening now during our era, if you want to say. And that's allowing us to get this breadth of information that can then feed into the models. So the time is now, I suppose. It's all exciting.
Great. Yeah, Aditya, do you want to say something to that?
Sorry, I just wanted to add to what Natasha said. I feel like some of the big stuff is also missing, and simply because it was just too hard to do. For instance, getting the interaction between the ocean and ice shelves, it just was practically not feasible, I guess. And other things like representing sea ice in the models is tremendously hard. It's a huge challenge. And Shenjie just showed us how important that can be to, when basically producing bottom water that can affect the whole global ocean. So some of the big stuff is also missing and probably getting better. Tide interaction with these continental shelves and ice shelves, again, another big thing that's missing. Ice shelf meltwater, again, missing.
But that also, those processes also involve a lot of small scale processes, right?
Right.
I think we just got a lot to learn, right?
Yeah, I guess that's the purpose of the SO-CHIC project. Are there any more comments or questions? I was actually a bit wondering about the maybe a stupid question, but what's the difference between the Weddell Polynya and the Montereys Polynya? Should maybe notice.
Do you want to take that, Holly?
Yes, I was trying to work out how to raise my hand as you all so politely did, but then I got muddled off. But yeah, so there's not a cut and dry definition. It can be down to the size of the Polynya, the duration of the Polynya, but ultimately Montereys Polynya is the smaller Polynya that we see more frequently, whereas the Weddell Polynya is a Polynya that spreads further over into the Weddell Sea. So it's much larger and much more sparse in the historic record.
And that's also
might...
the, oh, sorry, go ahead.
No, you were saying? I was just adding to Holly's point that the Montereys Polynya, depending on how you define it, it might actually be even more frequent because it's a region with generally weaker sea ice, the halo region. And if you looked at sea ice thickness, for instance, which of course we don't have very good observations of, it might actually be much more frequent. And also, in many years, you find when the sea ice starts receding, you find early melting in the Montereys region. So again, depending on the time period that you sort of define your Polynya to have occurred within, and if you have this early melting outside that time period, it wouldn't get counted as a Polynya. Do you only count it during months of September or October? Do you not count it if it happens in November or December? You know, there are all these, but it's just a region with weak sea ice in general.
But I guess we would expect much larger impacts from the Weddell Polynya compared to the Montereys Polynya.
Right,
Yes.
and that's probably what the Gordon paper, Chion and Gordon, sort of hypothesized, that it was because of increasing freshening in the Southern Ocean since the 1970s. The Polynya doesn't spread as much as it did back in the 1970s.
So you might have noticed a few discrepancies between our presentations, and that's because there is still a lot of debate in the literature as whether or not the 2017 was just a Montereys Polynya or whether it counted as a Weddell Sea Polynya. And some people say it does, and some people say it doesn't.
And I guess the one that opened before the SO-CHIC cruise was a Montereys Polynya, and maybe not as exceptional as if it was a Weddell Polynya.
Yes, the 2021 Polynya was much more short-lived and was much more localized to the Montereys. So we would count that as a Montereys Polynya.
Okay, yeah, thanks for clarifying.
Can I intercept a little bit?
Please.
So I think, I feel like we're nearing the end a little bit of the session. I think we've had great presentations and a nice discussion. I don't know, Nadine, if there's something you want to do to wrap it up. after that?
Well, I would
Right.
definitely like to thank all the speakers and the great presentations, nice insights into the SO-CHIC projects, the results that has come out already, and also talking about the future plans for the next half of the project. And yeah, I think it's exciting work. So yeah, thanks, and you can go ahead, please.
I would like to thank you very much too for being able to moderate, because that's been very nice. I think you did very well with the discussion, so that's very nice that you were able to do that. Before I fully close off, I still want to do a very small promotion part for another part of what we're doing in the SO-CHIC project. We're organizing a cartoon competition. Sounds a little different than what we're doing. So let me slide this screen. Just as a little heads up for anyone involved in the SO-CHIC project, or somebody who's familiar with it but not involved with it, we're organizing a cartoon competition starting in September. The details will be on the website, but we would just already like to announce the competition. It's going to be quite nice. There's a prize. Also for the exact prize, keep an eye on the website too. But it's definitely a prize worth keeping an eye for out. So just so you know, more information will come soon on our channel. So that's all. And yeah, I would also really very much like to thank everyone for your time and your effort and your very, very nice presentations. The session is also recorded, so we'll discuss with SCAR. It's going to be able to be online somewhere. And yeah, for now, again, thank you so much for being here. And I hope everybody will have a good rest of this summer. Or already a good beginning of the next working September, because I think some people are just coming back from leave rather than going on. But so thanks a lot. For me, that's it. I don't know if anyone else has something to add. Otherwise, have a very nice day.
Thank you, Piotr.
Thanks, guys. Good to see you.
Thanks, everyone. Yeah.
Thank you.
Yeah, thanks for arranging this.
Cheers.
Bye.
Bye.